So good morning, good afternoon and good evening to the second Matrix online seminar, wherever you are in the world. Today it's my pleasure to introduce Professor James McCaw from the University of Melbourne. James is a professor in mathematical biology and he's a member of the Australian Health Principle Protection Committee, who advises the National Cabinet in Australia about measures to take with respect to the COVID-19 pandemic. Before we start, I'd like to acknowledge our sponsors, the Australian National University, Monash University and the University of Melbourne, and the ASC Centre of Excellence, ACEMS. Just a point of order, we'll have the seminar run for 45 minutes. If you have any questions, you can submit them through the Q&A box at the bottom of your screen, and we'll go through the list of questions at the end of the seminar. So no questions during speaking time. Tom has put on the next online seminar, which will be given by Maria Chudnovsky from Princeton University on the 2nd of June. So I hope to see you back then. So now I want to hand over to James, who will speak about mathematical modeling of infectious diseases.
Right, thank you very much, Jan. And I will start by sharing my screen and putting up some slides. And well, for me, it's good morning, and I'm sure for many, it's good afternoon or good evening. So thanks for the opportunity to speak today. Share screen. Okay, so thanks for the opportunity to talk. What I'm going to work through is how mathematical modeling and data and analytic techniques associated with our models have been used. I'll touch on around the world, but primarily I'll be talking about how the models have been used to support preparedness and also response week to week, day to day in Australia to date. So I'm going to start because of the broad audience. I just want to say a little bit about emerging infectious diseases and pandemics, just to put the events that are currently going on in the world in some context. And then I will say a little bit about the early emergence and global spread of COVID-19, including some very simple calculations that were done to help the world understand that it might be faced with something rather severe. And of course, we've seen that now play out. And then I'll talk about how we use scenario modeling to inform preparedness and early response. And then more recently, nowcasting and epidemic forecasting, which are techniques to study data to inform the measures and the health system requirements. And all of this really got going in around, or my involvement and that of people like me around the world started in mid-January. Which isn't very long ago, but I can tell you feels like a long time ago for me. So just before I start on the current pandemic, pandemics are not new. They've been part of human history for as well. Pandemics and the spread of infectious diseases is something that's just tied into the fact that humans are social beings and we live in a broad ecosystem. There are studies of social distancing in the 14th century with plague and the Black Death in Europe. Not quite so far back as that. I spent a lot of time earlier in my career studying the 1918 influenza pandemic. And this slide's just there just to really point out that the imagery we see on TV today is, so on the right side of the here, we see similar pictures today, shockingly. And also that the other thing is that we see different epidemic waves. And so we might have seen the first epidemic wave of COVID-19, but the underlying reasons for why we get these waves is, well, there's a few different possibilities, but one is that our social distancing measures suppress infection, and then when we relax, we get a resurgence of cases, and so that's a highly plausible explanation for what happened 100 years ago, and is plausible that that's what we potentially will be faced with COVID-19 over the coming weeks and months, either in Australia or globally. And then on the left, I've just put something from one of the newspapers at the time showing, and the detail doesn't matter too much, but each row is a different major capital or major city of the United States. And it shows the burden, it shows the percentage of the population that were dying within a few weeks, different periods of time. So it's a little bit, you've got to do a bit of manual accounting to figure out what the rates there are, because the denominator, the time periods are different. But one of the interesting things that we observe, and it puts a cautionary tale on how we analyze any data at the moment in our current epidemic, is that across different states and cities of the United States, there's a really distinct difference in the proportion or the number of people who are dying, even though the virus was spreading quite uniformly. So there's a lot of variability in how epidemics spread and how they impact on societies, which is not necessarily well explained yet. It wasn't then, and it remains difficult to do so. This is something that I've been thinking about for quite some time. So I just wanted to sort of put a few of these things in context of work that's been done, primarily at the University of Melbourne in Australia, and that's where I've been involved in it, but with work done across the world and through many groups across Australia as well. But this is the work I was involved in early, which was, so this was sometime around the 2009 pandemic, but where we were trying to work through some of the ideas around how influenza spreads, how immunity might modulate that spread, and where the risks are for future pandemics. And in that paper, we actually explored not just the 1918 pandemic, but we went a bit further back, part historian, part data analyst, part mathematician, and looked at pandemics that you can find in the historical record right back to the 17th century and all the way through to the present day. And you can pick out from the records, particularly in the United Kingdom, back a few hundred years ago, there are excellent parish records of death registers, so you get really good information on deaths. And you can see some of the numbers in here, and you can see that this mid-19th century epidemic was incredibly severe. And this actually put some imprinting on the population, so that people who survived this mid-century epidemic were relatively protected in 1890, and indeed there are patterns of exposure in early life that lead to protection at the next time there's a pandemic. So you can see for influenza, there are regular, but if not sporadic, event through around the world. There's some shocking numbers in here that I draw your attention to. In Alaska in 1918-19, 600 per 1,000 people lost their life, and in Indigenous populations, 42 per 1,000 lost their life here in New Zealand. So there are huge heterogeneities in terms of risk given exposure. So the other event that has been incredibly important in driving methodological developments in mathematical epidemiology and infectious disease modeling is SARS, which happened quite some time ago, close to 20 years ago now. And SARS is interesting for two reasons. One, it's an incredibly similar virus to what we're faced with today. The other thing that makes it very interesting is that we, being humanity, in a sense, beat it. Over here on the right of my screen, which is unfortunately covered by my Zoom pop-up window, so I'll just move that across so I can see what I'm talking about, is the epidemic curve from SARS. And there's two things about this. You can definitely see that as a global community, we flattened the curve, so to speak. This is the worldwide epidemic, and you can see that there were some events where there was a huge number of infections recorded on a single day. And this is because SARS had a very heterogeneous offspring distribution. Most cases transmitted the virus to very few people, if possibly no one. And then occasionally we had people who spread the disease to a large number of people, so super spreaders. This was actually helpful in that once you understood that and you had good infection control practices, you could focus your efforts around preventing transmission from those who seem to be doing most of it. SARS was also incredibly severe. Be aware of the two different axes here, but it killed a large proportion of those who were infected. So SARS was an event that alerted the world to the absolute need to be better prepared for epidemics and to think about how to manage them. And indeed really stimulated the development of investment in mathematical epidemiology and infectious disease dynamics as a capability that would help keep populations relatively safe or help mitigate the impact of emergent diseases. 2009 H1 influenza was, in a sense, looked and has ended up to be a dry test run. Since then, it was a global pandemic, but it happened to be with a disease which, on average, at least, was sufficiently mild that it didn't cause the world to respond, or the world didn't need to respond as it has for the virus we're dealing with now. So I just want to go back to December 29th last year. And there were recorded 4 cases of pneumonia in Wuhan. Indeed, the only reason these cases were identified and noted so clearly is because of a surveillance system put up in the following SARS to identify potential new issues. So these cases were identified through a SARS-based system. And they were all linked to a single market. There was environmental samples were positive for virus, but there was no animal source. A month later, there were a few hundred cases of the pneumonia had been recorded, and they were confirmed to be due to a novel coronavirus. In fact, the coronavirus had been identified in early January. And I think it's my next slide, but what became clear very quickly and was clear by mid-January was that this couldn't be simply something what we'd call a zoonotic infection. It wasn't that there were hundreds and then thousands of people being infected by a single animal or environmental source. It was clearly spreading from human to human, and the earliest initial estimates of the reproduction number, which I will define shortly, was that it was around 2 to 3. So this is on the 16th and the 17th of January, the WHO called an emergency meeting of a whole bunch of infectious disease modelers from around the world. In Australia, Jodie McVernon, and who's a professor of epidemiology at the Doherty Centre, and I were invited to that call. And the WHO reported on some of the cases, and then Professor Neil Ferguson from Imperial College put forward a very simple calculation, which I'll show you in a moment, or sketch in a moment, but just simply made the argument that, so we'd identified on the 16th of January that there were 3 confirmed cases of this coronavirus in travelers, 1 in Thailand, and 2 in Thailand and 1 in Japan. They were Chinese nationals. They'd been in Wuhan, and now they showed that they had the virus in overseas. And this was at a time when there were only reported and known to only be 40 odd cases of this infection. And it's a very simple argument that if there are 19 million people who might catch a plane from Wuhan International Airport and 3,300 depart per day, then to find 3 of 41 or 3 of 44 all happened to have chosen to leave the country and then be noticed in Thailand or Japan is highly unlikely. So taking account of some of the biology of the disease, which would be that it takes a while before symptoms appear, and that it takes another few days before, given you have symptoms, that you seek medical attention. You can do a very simple probability calculation to say, well, there aren't 41 cases. In fact, the maximum likelihood estimate for the number of cases, just by looking at the binomial probabilities, is somewhere around 2,000. And indeed, 4 days later, 17th, 5 days later, by the 22nd of January, when we'd had about our second or third meeting with the WHO, based on this Imperial College note, Chinese authorities looked deeper into the potential outbreak and had identified 440 cases based on 7 exported cases within just a few days. And so this gave us very strong evidence very early that this was something that was almost certainly spreading, and spreading fairly rapidly. And the question was, where was it going to take us? Okay, so how do we deal with this as infectious disease modelers, and where does the mathematics come into these questions? So early on, a lot of the questions are about risk and the probability of establishing outbreaks in different regions in countries. And this is something that our group's been thinking about for a while, along with many other groups. At the moment, I've just shown you a paper that we did in collaboration with the Department of Foreign Affairs and Trade during the Ebola epidemic, where we looked at the probability that Ebola might make its way into the Asia-Pacific region, and then what the probabilities of detecting those imported cases might be, and then what the capacity of their health system to respond would be. I won't go into details, but I just thought I'd flag it there. And then most recently, and rather strangely, we published this on the 9th of January this year, but it was work we did last year, was we wrote a paper, including in collaboration with my colleagues in Adelaide, on how pandemic planning and response efforts fit together, so that mathematics and computational statistics fundamentally can come together to help guide response options. And the framework that we work through there has sort of been used in, day out since then. So the way that governments respond to pandemics is through instruments and tools, which are written documents largely. These instruments are informed by a whole range of different scientific and public health expertise, and potentially economic ideas. And the Australian Health Management Plan for Pandemic Influenza is a document that's evolved over decades now, and is heavily informed by the use of mathematical modelling to provide plausible scenarios that the government might need to respond to, and then articulate how different types of interventions may change the transmission of the virus, or whatever the pathogen may be. And in very early February, that plan was adapted, including through some assistance from people within the Australian modelling community to become the COVID-19 plan, which is a public document. So just before I go on to the actual little background on the mathematics, because I just wanted to make another comment, which I think is a really important one in terms of how, not necessarily just mathematics, but how science helps contribute to response policy and has made a difference in this event. So, and there's a huge change COVID-19 compared to what I saw about a decade ago. So in 2009, I know when I was trying to help and supporting the Australian government in the response to the influenza pandemic then, most of what I was learning from the scientists was coming through the peer-reviewed literature, where I would read a paper in a journal. Often it was an important paper or a topical paper, so it might appear in a very high-profile journal, but that was when I really first found out about it. And people in my community found out about it. And often that meant it was a month, 6 weeks late. It was about the situation some time ago. The world is very different now. It started changing with, at least in the field of infectious disease epidemiology, it started changing around the time of the Ebola epidemic in 2014 in West Africa, where groups have become incredibly open in describing their work to others around the world and putting their work up on public websites and on preprint servers. And this has been absolutely fundamental to the ability of scientists all around the world to gather early information and present that in the appropriate ways to the decision-making authorities within government. As I just showed you before, the work that came out of Imperial College on the 16th of January it is a note on their website, but of course was very influential in driving the world to take this seriously. So we now have preprint servers in medical science, which reminds me of my background in theoretical physics, where preprint servers have been there, or in physics more broadly, for a very long time. And indeed, the Imperial College London website and the London School of Hygiene and Tropical Medicine website have now got dedicated COVID-19 pages. They've had them for a few months now, and all of their work, as soon as they believe it's sort of sufficiently reliable, is up on these web pages. You can see them developing their manuscripts in real time. They're sharing the information, they're sharing computer code. And indeed, you know, there's almost near peer review on Twitter at some stages. And what this means is that access to information is timely, and it's saved lives fundamentally. So I think it's a very interesting comment on, or observation, I'm not the first to make it, of course, about how the way we do our science can directly influence its utility, particularly in these acute types of events. So I'm not going to assume that everyone or anyone knows. I know some of the people on the call will certainly know, but won't assume that anyone knows what the actual fundamental building blocks of the mathematical models we use here are. So I'm just going to sketch it out, and I'm also deliberately sketching it out in a similar way that I do if I talk to high school students, because I think one of the other things that this event has shown us, and that I would like to communicate to my mathematical colleagues, is that that in the most unpleasant of circumstances on this occasion, we've also got an opportunity to demonstrate how our skills are applicable to problems in the real world. This is something that we always know, and it's something that there's an opportunity here. So I have, for a long time, also tried to teach infectious disease modeling, or demonstrate how it might work broadly to high school students and others, because fundamentally it's a nonlinear dynamical system, but it's something that is accessible if presented in certain ways to middle high school students, I've found. So I'm sort of going to try and show it in that way. Of course, when we do our science, we do it in the most, in sort of, I won't say rigorous, but the more precise ways in terms of the simulations and computations. So the fundamental starting point for how we think about how a disease spreads is that we look and we can see that the population, any individual can be in one of three mutually exclusive states, being either susceptible, infected and infectious with the virus or recovered from it. Different viruses obviously have different or other possible states that one could be in. HIV has a long period where you are infected but not infectious necessarily, or the opposite actually. So different states, but the starting point is this SIR model. And so as mathematicians, we abstract, and we, computer scientists might spend a lot of time doing some simulation-based models with agents, and we use those as well. But from a mathematical point of view, we abstract and we just say, well, we have 3 compartments. Abstract again, I don't care about the sizes of them. And then what we do is, at least if we have large populations, we ignore stochastic effects, we can just write out a set of differential equations. So in some continuum limit, so we ignore the individuals completely, and we have a set of, in the simplest possible way, we have a set of nonlinear differential equations. Apologies for writing them in PowerPoint here. I assure you they're normally written in LaTeX. And where we look at the flow between these compartments are the black arrows, and there are infections and recoveries. And it's worth just looking at these equations for a little while, because they are, well, there's no known solution to them. And so we can do some nice, this is a 2-dimensional system, of course, because there's a conservation law. So you can study this system in the phase plane and in typically the SI plane, and you do some nice nonlinear dynamics and stability analysis, which is an excellent introduction for upper undergraduates to understand how a disease spreads and why it does. And there's some nice calculations you can do with this model. I'm sort of going to leave them as an exercise for those who haven't seen them. But they also just point out that fundamentally a key tool in the work we do for government and others will come down to being lots of numerical systems, because as the dimension of the system gets higher with more than just S, I, and R, the nonlinearities remain, and we're looking at the out of equilibrium dynamics, and so simulation is the way to go. Just on the right here, I want to point out, and you can see it by inspection in this simple model, if we look at the equation for the rate of change of infectious people, so dIdt, if we just factor out gamma I, we can see that whether or not the number of infectious people is increasing or decreasing depends on this parameter R0. Of course, through time multiplied by S over N, but at the beginning of the epidemic, if S equals N, then we have dIdt is just proportional to R0 minus 1. And so if R0, it clearly is a threshold parameter, indeed it's a bifurcation parameter of the model, and if R0 is greater than 1, we'll have an increasing number of infectious people, and if R0 is less than 1, we will have a decreasing number of infectious people. That argument follows through to all sorts of other models, and it applies within stochastic models and all of the other sorts of models that we use in this space. Of course, through time, what happens to an epidemic if you just let it run naturally is that the S here, the S is decreasing, and so you get to a point in time when the susceptible fraction is 1 on R0, and at this point in time, the rate of change of the infectious compartment, so that's the incident number of new cases, is equal to 1. And this defines the point at which the epidemic has peaked. And then from that point onwards, the epidemic will decline, at least like clockwork in these deterministic models. So this, and there's more analysis you can do on this. It's very nice problems to set like undergraduate applied math students, and you can unpick this further. But fundamentally, this sets up the way that we think about how these diseases spread through populations. And very deliberately, as I said, we can, if we write those equations just as discrete time difference equations. They're something that you can give to a mid-high school student and help them understand why those equations capture the spread of the disease, and you can put that into Excel. So I've deliberately put this up as an Excel figure here to show that you can actually, it's an excellent pedagogical tool. Essentially, it's just doing an Euler solution, and students can run that through, and they can discover fascinating things that might surprise them, such as that at the end of an epidemic, there's lots of susceptible people. That yellow line is, you know, it's only dropped by about 60% or so. So simply by constructing those equations, which is something that you can work through as a matter of logic, and then thinking about how you can run them forward day by day or hour by hour or week by week in a like through a spreadsheet. Students can discover these sorts of behaviors and appreciate them, and as can public health officials, I would say. And the other thing actually that this, for the more inquisitive students who do this, is they then start making something like the infectiousness, this beta parameter stronger, so the rate's higher, and then they can break their Excel simulator, and they realize that you need, if there's something that's a high rate of change, you have to take a small enough step size to keep the errors under control. So I've definitely seen students discover something about and really gain an understanding by seeing things break. Simple tools which fail can be incredibly instructive. Okay, so moving on, that's kind of the building blocks of where a lot of our work comes from. I just want to cover a few more of the actual events that have occurred. So this is a paper published in the Lancet in January, and it was done by Gabrielle Lung and Joseph Wu, with some broadly some of my colleagues in my international network who work in Hong Kong, and Gabrielle in particular is one of the critical people in our global community who understands both how governments work in these spaces and how mathematicians and statisticians contribute. And what they published here early on, based on knowledge of how people moved within China and what the behavior of the epidemic in China was, is they made some very short-term forecasts of epidemic activity using a kind of SI model, but with multiple different models coupled together, to predict over here on the right where the most likely places that the epidemic would be seeded based on global transport networks. And if you look into this paper and a little bit more detail, this was presented at another WHO call that I was on at about midnight on the 30th or 29th of January. And in that top 20 list of destinations were Melbourne and Sydney in Australia. And so after that call, Jodie McPhern and I drafted an email to our Chief Medical Officer of Australia saying, look, here's a paper that shows how model-informed risk of where the virus might spread through China. We've noted that high on the list of places where it might arrive at the two major transport hubs in Australia, and within about 24 hours, the border with China had closed in Australia. And that then set off a sequence of meetings in Australia with the Commonwealth around managing what would be potentially the risk of this virus. Some of the earliest work we did, and this was driven by Freya Shearer at the University of Melbourne and Nicholas Geard in computer science at the University of Melbourne, and with some critical input along this pathway from Andrew Black from mathematics at the University of Adelaide, is we set up a framework. We thought quickly. This whole workflow took about 2 days to develop, or maybe 3 days, where we looked at the outbreak size in China, and that was being predicted and projected forward using just a simple exponential growth model. We then used global transport network data to look at what the importation risk from China into an intermediate country in our region might be. So we were looking at, well, if we block the border to China, where's the most likely way that it comes from China to somewhere else through a traveller who then travels onwards to Australia? And so most of the connections, either people come from China directly to Australia is dominant. The other routes into Australia from China are via countries in the Southeast Asian and Western Pacific region. And so then what we looked at is, so what was the number of potentially undetected cases in those intermediate countries, using a statistical model, again, as a preprint that was done by some people in the United States. We then used, and this is where Andrew Black was involved, we used a branching process model and the supercritical, so a growing tree, to look at what the probability of having an outbreak occur within those source, intermediate source countries would be. We fed those simulations, I'll show you some in a moment, into an outbreak size calculation, and from there put together a risk assessment for the Australian government, and we updated it 3 times a week from early February onwards, showing where we thought it would be most likely that we would have an arrival into Australia who had the disease. And this is the sort of work, I think this is what we showed them on the 19th of February, but we were showing them, the government, these 3 times a week from very early February onwards. And what they broke down was that, you know, the red bits were the parts to pay attention to, and we broke down all of the risks. So you can look at the paper if you're interested in more detail, but I'll just take off as sort of one example of a place which was very sensitive at the time, and it's now much easier to talk about, which is that Indonesia was reporting on this date here that they had no cases of the coronavirus. Our models had a probability of 1, and it is distinct from 0.99, so this is 0.999999 something, probability of 1 that they had established local transmission. In fact, we would believe that they would have had, you know, somewhere in this range of numbers of cases, and then given the number of people who arrived from Indonesia into Australia, we had a very high risk that this is where we might establish infection from. And you can see a whole range of other patterns where, so Thailand had a very high number, like lots of links to China. They had cases, we knew they had cases, but there was less air travel, and so perhaps a lower risk. So this work was very important in helping the government manage its borders as closely as it could. And so, you know, we also, there's a bit, just a little bit of a hint of the sort of computations and calculations that are done here. I'm aware of the time, so I'm going to skip over this. I've gone way. Anyway, so the other thing that we were also doing at the same time as looking at that risk assessment was trying to think about what an epidemic in Australia might look like. And so this is using a slightly more fancy, but still very simple SEIR model. And we took the values of the reproduction number that looked like from China, around 2.5, and we fed them into an epidemic model where we had high severity. So this is 1 in 10 to 1 in 100 of the people infected will show severe symptoms. And this is very mild severity, 1 in 10,000 people show symptoms. And we put these curves in front of the government, and it emphasized how strongly these are huge epidemics. If we reduced how much the virus spread through some, at this point in time, unknown method, but social distancing perhaps, by some moderate amount, only 25% reduction, we could smooth and flatten these curves. And this is what helped the government both understand that these numbers here were terrifyingly large and that we could do something about it. The details of that model are here. So this is a diagrammatic picture of the differential equation model we have. It's just to emphasize all of the detail. You can, of course, look at the preprints. But this disease has quite a lot of biological structure to it, and to do effective modeling for scenario planning and analyses, you need models that have this level of biological fidelity. So we have susceptible people. They go through an exposed phase when they're in they're going to get the infection, but they're not yet infectious. And we need to be careful about from a probabilistic point of view, what the transition time from here, from S to I is. And so if you split this up into multiple compartments, you change the hazards going through. So it gives you more realistic simulations. Infectious people, if they're detected and monitored, they're put into isolation at some rates, or some fraction are noted and occurs at a rate. They then recover. Otherwise, you go on to a late stage infectiousness. In this model, and I won't go into the details, there's also ways of saying, well, when you identify these people, then you who are isolated, you also can put their contacts, their close contacts, into quarantine, which is these superscript Q states, which then have a very similar structure. And so clearly with these sorts of models, you have to definitely have to resort to simulation. So we use those models, which give us a pattern of the number of infections over time. We then have to feed those into a model of, well, what happens to an infectious person? Where do they go in a system? What do they do in a health system? And so there's a pathway of, do people have symptoms? Do they seek consultation? Do they need an ICU bed? And we feed all of this through, informed by Australian data. And what this allows us to eventually do is get to simulations, and we do tens of thousands of simulations that show, one, what an uncontrolled outbreak might mean in terms of ICU bed demand, new needs for ICU beds. And when we put this curve in front of the Principal Protection Committee and ultimately the National Cabinet in very early February, this is what got their attention. The idea that you need 35,000 new ICU beds every day when we only have 5,000 in Australia was of concern. Of course, we were also showing what we thought we might be able to achieve through various intervention measures. These numbers here are still pretty challenging. So if you do lots and lots, there's a huge amount of uncertainty on the parameters of all those models. So you do lots and lots of simulations in a big Monte Carlo system. And I've gone way over time so far, so I'm going to skip over the detail. But what we do is look at where, under different intervention strategies, 5 times increase in ICU capacity. These are the duration of excess demand, and you can see that the median of many simulations is that we would never exceed excess demand with ICU if we had a reasonable level of social distancing in place. Of course, we now know that we've achieved much better social distancing than what this allowed. And so we then show that these are the sorts of figures, and the analysis, the interpretation of these numbers is what helps the government decide how much it needs to expand its ICU capacity by. So it's a mix of some mathematical modeling, lots of numerical simulations, and then this interpretation layer. So in the last couple of minutes, I'd just like to explain that was all of that work is done ultimately prior to having any meaningful transmission in Australia, and it was all back in this period of time here. Once, and so it's about scenarios and planning. The other place that the kind of skill sets that people like me and the 40 odd people who are now working in Australia on the response have is we work on studying the actual data. So this is the breakdown of the epidemic curve in Australia. And I think it's broken down in up until 2 weeks ago, it's close enough. It's broken down in a way that's fundamentally important for understanding what's going on in Australia at the moment, which is we've plotted it by overseas acquired, which is the dark bit, and then the locally acquired, which sits on top of it. And what you can see is that Australia experienced an epidemic driven by returning Australian travellers, well, and others, but predominantly Australian citizens returning from overseas. And why were they, we locked the borders down, but they were coming back because it's their right to, of course. And there was a huge amount of epidemic activity occurring overseas. And so we saw lots of importations. And so that's what drove some of the policy responses here around quarantine of arrivals. The other thing you can see is that the blue bars don't actually grow that much. They do grow, so they're expanding here, which means that there was never a sign in Australia that we had totally out of control, widespread transmission within the community. This is a public health issue, but it's not a local transmission issue per se. And so we can analyze that through analysis of the effective reproduction number, which is the number of secondary cases caused by a primary case at a particular time, accounting for all of the interventions. And so we actually analyze these through statistical methods, which essentially by looking at what we know what the time from infection symptoms to symptoms is in the statistical distribution of symptoms to symptoms is, I'll finish in a few minutes for questions. We look at those serial intervals, that distribution of the serial intervals, and then we look at the overall rate of increase of the number of cases, and then we can map from the time from person to person to using the overall exponential growth rate, we can figure out what the number of offspring from each case would be. And the way we're doing this is working with the London School to adjust some of their techniques to account for the importations, which is such a key feature of the Australian epidemic. And what it allows us to do is produce these forecasts of the reproduction number in different states. Just to draw your attention to this, what they show is that we successfully got the local reproduction number under 1 in Australia sometime in mid-March, and depending on the assumptions you make in these analyses about infectiousness of local cases versus imported cases, you can move when this cross this critical line. You can detect the local Northwest Tasmanian outbreak, so we knew this was occurring around the same time that the public health authorities did. And the other thing that you'll see is this method fails because it's a Bayesian method, and we can see this returning to its prior distribution towards the end. It fails when there's no data, but that's a good thing. That's a good problem to have when there's very, very few cases in Australia. There's nothing to predict. And so this is starting to just fan out and return to its broad prior. So doing forecasts at the moment is challenging. So here is a forecast, and I'm aware of the time, but here's a forecast from the last time that we could make a reliable forecast, which is about a week or so ago, showing continued decline of the epidemic, given the reproduction number. The counterfactual here is if you relax social distancing measures around here, we'll see an explosion. And we can also look at projections of prevalence of hospitalized and ward occupancy cases by drawing on the age distribution of infectiousness, the clinical severity spectrum, the length of stay data for people in hospitals to try and do a projection of hospital load. These methods are hard to develop. We're still working on them primarily so that if the epidemic does resurge in Australia over the coming months, which is of course a possibility, we will have tools to deal with it. So my conclusions are just around how models have been used. I haven't gone into much of the mathematical detail, but it's mainly just nonlinear differential equations. And I haven't said anything about exit strategies. Happy to take questions on it. And very importantly, there's a large team of people who have been working on this in Australia and supported by many different groups, including health, defence, DFAT, and across at least 7 or 8 institutions. And so the names on the screen are where the majority of the work, actually hard work, has been done by those people. My focus has been about trying to translate those bits of work into the decision-making context within Australia. So thank you. I'm sorry I've gone about 10 minutes later than I had planned.
That's right. Thanks very much, James. I'll applaud on behalf of everyone. Always a bit quiet at the end of a talk. So let's go through the questions then. So there's a list at the Q&A box. So the first question is, why were there gaps in the data in the global SARS epidemic?
Oh, I have no idea. So these are on the daily incidence data. So I'm not sure. Good question. It's a long time ago. One thing I would, you definitely see in, I'm not sure it's the case on this one, but a lot of infectious disease data has a weekend effect that like no one records stuff on Saturdays and Sundays. I'm not sure if that was the case on that one. It may also be that there were some parts of that epidemic where it never got to huge numbers. And so there may possibly have been days where there were no recordings.
The next question is about Sweden's strategy. Do you have any comments on that?
Yeah, so I do. So there's three, and my last point on my conclusion slide was about where we go from here, which is really another talk. But there's fundamentally three different things that we could possibly do right now with this virus. One is we could try and lock down harder and eliminate the virus. That may happen in places like Australia and New Zealand. It looks like in the last 48 hours, it might have happened in South Korea. Those elimination strategies the idea is that you literally get rid of the virus and then you can go about moving around. Of course, what it does is it leaves the population almost fully susceptible. Far less than 1% of Australians have been infected yet. So that's one possibility. So I'm getting to the Sweden thing, it's just complicated. The other approach is a suppression strategy where we try and keep epidemic activity at such a low level that we minimize the number of avoidable deaths, but we allow enough movement and activity so that we don't do more harm than good in terms of the economic and social implications. That relies on fundamentally having a vaccine come along at some time to provide some protection. The third option really is that we try and manage quite a large amount of infection quite rapidly to try and get the population up to this herd immunity level, which is essentially the idea that enough of the population have got the virus so that if there is a new case, it can't spread. So this is where S goes to 1 on R naught, like I said from the simple SIR model. And in a sense, Sweden is taking that approach, although not in a but in a managed way. The advantages are that it means that they understand where they're heading in terms of getting to a stage where the population has a natural level of protection, that it's sort of the virus won't spread too much. The disadvantages is that you are locking in some morbidity and mortality, which you may be able to avoid by waiting out for a vaccine. Also, if there are issues around how long we're protected for, those strategies might be risky. So, I mean, I'm not going to say it's good or bad, except I think it's almost an ethical problem as much as anything else. It's a very difficult problem to work through. It's not what's going on in Australia at the moment.
Okay, thanks, James. There's a few more questions, so I'm going through the list.
Mm-hmm.
Can you comment on the current situation with Ebola?
No, I can't. My mind is so focused on coronavirus. I'm not comfortable, or I'm not across enough of the issues. I will say one thing though, which is, so not about Ebola directly. There is a valid and huge concern that with all of the public health and political attention directed towards coronavirus, that critical health control programs, often to do with other infectious diseases, are at risk. So I'm involved in a malaria consortium, and it's already quite clear that some of the efforts around eliminating and controlling or eliminating malaria are being put at risk by the limited resources being redirected towards coronavirus. There will be concerns around polio eradication programs and the resurgence of other diseases, drops in vaccination rates for children, possibly also increases in them. It depends on how systems respond. So there's a more general point, which is that this event will have complicated and hard to predict, but likely negative effects on other strategies because of limited public health resources.
Okay. When you were talking about the risks associated to traveling, here's a question about the risk of importation from the US.
Yeah, so clearly it was very high at some stage. So the tool that I talked about was used very early on, and it was very clear when that tool, and it was by mid-February, where that tool had reached its limits, because the fundamental starting point for that tool I described is that the only place with the key place with transmission was China. It was seeding it to places, and then they were feeding it back. And the idea was primarily around how people move from China to Australia. People don't come from China to Australia via the US. Typically, when they do, if the prevalence of disease gets high in either Europe or the United States, the whole principles of how that system break down, because you actually have to worry about direct travel from the US to Australia or from Europe to Australia. And so it was clear that that was what it was getting to by early March. I forget exactly where it was. And that's where the discussion around how to manage borders within government shifted to deal with precisely what you're pointing out, the question is pointing out. One thing I would also say is that the US has been a very sad to watch and complicated what's occurred there has essentially been a public health disaster, and thankfully it looks like they're slowly getting on top of it. Clearly, in hindsight, there are some things that might have been enacted earlier in terms of border controls for the United States. I can assure you at the time it wasn't so clear whether or not they were doing so well or so poorly at detecting cases.
Yeah. There's still quite a few questions to go, and some people have to leave at 9. So maybe you can go quickly through the rest.
Yeah.
How do your models take cruise ships into account?
They don't. The models don't. The models look at cases which are coming from imported cases and local cases. The cruise ships are a part of those imported cases. Of course, public health response takes a different view. There's many other things that go on with understanding the epidemic activity, but not everything is folded into every model.
Okay. Are there simulations based on event tree analysis and Monte Carlo simulations?
Event tree analysis and Monte Carlo. So the way that the simulations are done for the disease transmission, often stochastic versions of the sort of differential equations I showed you. So they're not exact. And then we would just do lots and lots of simulations to look out over both the stochastic variability of the system, but also because we do lots of the parameters change. I guess to understand more about exactly what we do, you could look at the preprints.
Okay, thanks, James. Given the significant majority of cases are overseas derived in Australia, why didn't quarantining returning travelers work?
I think quarantining. No, I think we worked. It did work. We averted. I think if you look at our epidemic curve, the locally acquired cases never grew at a dramatically high rate. The reproduction number, even in late February, early March, was only just a little bit above 1, which instead of 2.5 to 3, which is because of the recommendations we had for returning travellers, which was to if they felt ill, to stay at home and to monitor their symptoms closely. There is, of course, always the argument of hindsight that if we had shut down every border on January the 29th, we would have had no cases, but I don't think that's a valid sort of way of looking at the epidemic. So we started early. Doesn't mean that you couldn't have started earlier if you had a crystal ball.
Yeah, there's still 30 questions, James. Just conscious of the time and your own time.
That's okay. I think it's an important issue.
In which extent were the forecasts of these models validated by future observations?
Yeah, so this is a really good question. At the moment, the forecasts, and if you look at other forecasting, is a very difficult thing for epidemics because we have such limited data. So we're still in the sort of practice phase of it fundamentally. The the number of cases in Australia, you could see from the forecast for Australia has, they're sort of, our forecasts are a little bit high, our forecasts decay a bit slower than what the case imports have. Of course, that's also driven by, we have to have a model of what the imports looks like, which is a bit hard to predict. So the models are okay, they're qualitatively fine. The detailed quantitative stuff needs a lot more work. It's a challenging area.
Thanks. So thanks for the great talk. Two questions. How do you define a reliable forecast? And two, what is the contribution of within-host mathematical models?
Okay. So defining a reliable forecast is tricky. I won't. I'm not sure how to answer that without quite a lot more thought. Within-host models are playing an important role, but more on the basic science side. In trying to understand how long people might be infectious for, whether or not when you measure someone as positive using a test, does it mean they're still infectious or not, which is both an empirical question and one way within-host models are helping. And this is an area of interest to me, but it's not something I've been pursuing in the current environment, but I know colleagues and people around the world are doing that. Part of vaccine development and things like that too.
Can you say a bit more about exit strategy?
Right. So I see this from Nalini. So I think I just touched on this really with what's going on in Sweden. I think where I personally think we should be heading are these suppression strategies. I think the extra effort to try and achieve elimination comes at a huge cost in terms of having to lock down harder. And my view is that even though we can control our borders in Australia well, we have natural advantages having the sea. It will come back in. The borders are large places. They're controlled by humans and humans are fallible. And so a suppression strategy to me is an appropriate one. We need to be adaptable though. So we need better forecasts and forecasts that we can sort of have a bit more trust in so that we can monitor where we're going over the longer term. I think if, in a sense, I'm assuming that at some stage we get a vaccine that does do something. If we don't, then ultimately the only path we have is towards one where enough of the population have been infected with the virus. I'm not sure if we should be trying to do that quickly or slowly at the moment. I think slowly.
Okay, thanks, James. So another question about validation. Do we have any data to assess whether our models' predictions are accurate? So a lot of models are of the nature, if we do this or that, then Y will happen. Could we validate whether our predictions were accurate? So you commented on this before. Is there anything to add?
Yeah, I don't think so. I mean, I think that they're exactly they're the questions we ask ourselves. So I think it's the right question. I don't think that the scenario work I showed at the start is work that's never a prediction. It's a planning exercise. The predictions are things that are coming out of the more recent work, like the forecasts. And of course, we can run those forward and see where the cases are going. Once you get to low numbers, it's hard to know. So there's a little bit of experience in seasonal influenza forecasting, and you might see how we're approaching it there. But there's still a lot to do here. In the United States, the best groups' forecasts of the epidemic trajectory don't overlap at their 95% credible interval lines. So it's hard.
Okay, thanks. Can you comment on transmission or lack thereof amongst children?
Yeah, so it's a curiosity of these types of viruses. It was true in SARS as well. There were very few children affected, and if they were infected, it was mild. It's becoming more and more clear. It's becoming incredibly clear now from the epidemiological analyses that while children get this virus, SARS-CoV-2, it is very rare for it to be severe. I'm sure at some stage there, of course, with enough infections, we will see severe outcome, but they're very uncommon. And analyses of outbreaks within schools, indeed in New South Wales, there was a preprint released last week, show, and other analyses show that children don't typically seem to spread the disease much at all. In fact, all of the New South Wales school outbreaks have been driven by teachers and parents. And so, I mean, I guess where this goes is about schools, and if there are risks around schools, it's primarily around how the adults in them interact, and how they might be managed. I think this is a good thing. If this was flu, which infects children severely, we would definitely have schools closed, and it would be a far more disruptive event.
Okay, the next question. R being close to 1 in Australia in March seems strange when the number of cases was increasing rapidly.
Yeah, so this is because the effective reproduction number measures how the disease is spreading within Australia. And it spreads within Australia due to local Australian transmission and transmission from imported cases to other Australians. And so our methods account for that. It's simply, it's like the imported cases are an input signal to then what the epidemic activity is. And so from a transmission system, dynamics, you've got to account for those importations, which is what the methods do. From a public health point of view, you care about all of them, right? But the way that you manage them is you manage the importations through the hotel quarantine measures or whatnot, or literally closing the border. The way to manage where the transmission is occurring is about the effective reproduction number, which was never much above 1 in Australia.
How does mathematical modeling incorporate or forecast for human behavior or responses to the pandemic?
Yeah, so at the moment, this is something that we've been doing over the last few weeks, is that we've actually got recently access to all sorts of interesting data around the number of people walking in parts of the city. There's public data, the Google mobility indices that people might have seen. And so we are now, and many other people around the world, are trying to use these data sets to tell us about how much we're moving and where we're interacting with people, to try and put those into the models of how transmissible the virus is, so that you get a model, mobility informed estimates of the transmission potential. And this should actually improve things like forecasts, and indeed these indices about behaviors, or these are about how we're interacting, can be one of the earliest warning signals that there might be an increased epidemic activity. There's more questions around how the psychological side of this and modeling that, and there are attempts at that, but it's very difficult to follow, I think, at the moment, through to something reliable about how my behavior might respond to, like, say, the number of deaths in the last 2 weeks or something like that.
Okay, the next question is a technical one about Monte Carlo. Some questions about number of realizations and validation. How do you justify the results? Yeah.
Okay, so so what we do is, by using as much data as possible from early on, I assume that we're talking here about the scenario analyses. We look at what data we had from China in late January and early February, and we try and get some understanding about what the distribution of possible values for things like the reproduction number might be. And then we do extensive sensitivity analyses on whether or not the virus may have had early infection before symptoms or not. And we build those things into the models. We do thousands of simulations, and we in justifying the result. Well, only there will be many of those simulations that are exploring parts of parameter space which are not true, because we're exploring possible future, like possible biological and epidemiological behavior. I'm not sure I'm understanding the question properly, but there is no way of validating the whole system. There is somewhere in where we've looked turns out to be what was true, hopefully at least, and other parts of it were plausible but not true, and you only find out once you've seen what happened. but I don't think I've answered the question very well, but
Yeah.
I'm happy for
It's another talk. It's another talk.
Yeah.
Let's go to the next one. How will Australia address antibiotic stewardship?
Antibiotics are about bacterial infections, and this is a virus. So I'm not sure exactly what the direction of that question is.
So maybe go to
Yeah.
the next one then. Maybe the question can be specified better.
Yeah.
About social distancing, why 1.5 meters?
Yeah, so this is not part of the modeling. This is part of how infection control and infectious diseases clinicians and people like that try and understand the world. This is a question for the biologist essentially, but it's incredibly hard to even think about how you can design an experiment to know exactly how humans spread the virus to each other. You can look at airflow, you can look at how far, projectiles, if I sneeze, go. There's all sorts of things like that you can do. And you kind of get to approximate numbers around, if you're more than 1.5 meters apart, then typically it's hard to infect someone. But of course, there are no detailed controlled experiments of things like that. The way these things fit into the models is not through that number at all. There is a transmissibility parameter in the model that tells you when S's meet I's, what's the probability of transmission, essentially, and there's a number in there, and it's a parameter. By tuning it, you tune the reproduction number. You learn about the reproduction number by looking at the big picture of the epidemic. So the models don't drill down to the level at all that you're talking about here.
Okay. So what kind of new modeling techniques will be needed now in Australia to support the analysis of different nuanced restriction relaxation strategy and options?
Yeah.
Given that so little data is available.
Yeah, well, so it's we're in an excellent position where the standard epidemiological tools are failing because there's no data to analyze. So like the effective reproduction number and things like that. So where we need to go, and people like Andrew Black are actually working on this right now, is methods to sort of look at the frequency and the size of clusters, so outbreaks, local outbreaks that are sporadic, to try and then pick up how the epidemic might be bubbling along in Australia, sort of say under a suppression strategy. It's a little bit like the difference between looking at a whole fire front and the dynamics of the spot fires. And by looking at the dynamics of all of the little spot fires, you might pick up a different picture, and that's where we are at the moment. And so that's sort of one of the areas where we need analyses. Of course, each one of those little spot fires is still a tiny little epidemic in itself, so it's going to be a stochastic epidemic simulation model.
Okay, thanks. Can we predict the cases in Africa and other poor health regions based on your model?
Well, so not directly on our model, but we are working, or parts of the Australian modelling community are working with our local low and middle income countries in Southeast Asia and the Western Pacific around trying to understand the capacity of their health systems to respond. I forgot to say during the talk that those models that we use have got age structure in them and demographics and risk profiles in them. So it's not just SEIR, but it's SEIR for all of the different age groups and then mixing between them. And so there are sort of standard tools in the literature that let you, take different population demographics and different risk structures and profiles and get the different epidemic dynamics. They're hard to validate. So we're using those in combination with the health system capacity in different low and middle income countries to try and understand how they might cope or not cope. And of course, there's going to be some very challenging public health situations across the LMIC countries all around the world. And we shouldn't forget that when we're in Australia or other very lucky places.
Okay, the next question is about the government's COVID Safe app.
Yeah.
Do you have any comment on that?
Yeah. So I've got two comments. I think I've installed it. That's the first thing I'll say. I've been involved in some of the development of it, and I understand some of the background to a lot of the security discussions. And you know, this app is designed to identify proximity, but not location. And I'm seen enough of how it's been developed to trust that that is the case. The real question here is, will it make a difference? So at 40% coverage, of course, if we all mix at random, then that's 16% of the interaction events will be between two people with the app, assuming you always have your phone on you. So it's then a very difficult question to push through. What proportion of contacts do you need to pick up on the phone system to know what the difference in a public health response is? And we have to wait for an experiment to do this. And those experiments and trials are actually going to be happening in Australia, where the public health units that work across the states currently, if they identify a case, then they interview the case, and then they collect the details of the contacts of the case, and then they ring them and they follow up. So this app will contribute to that workflow, and it is an open question because it's a question of the process, which is, will that app contribute and help in that workflow? Will the app be picking up people who the interviewers would have missed? And until we see what happens in the real world, we won't know. I think there is good reasons to think it could help if there was high uptake. And so it's worth an experiment.
Thanks, James. So the next question is related. How will data from the app go into your model?
Excellent question. So they won't go in. I think picking up on a few of the things here, the models we have are ways of helping us think through. So there's no one model that includes everything, at least not in the way that I don't see a huge value in having a model with everything in it, because there's too many layers of abstraction. However, there are some models that have looked at, well, how about this? There are some models that look at how delays in contact tracing will reduce the efficacy of quarantine, and you could put that into our model. So then it's an empirical question. If we learn how much the app increases the speed and the coverage of the contact tracing, it would just lead into a tuning of one of the parameters in our model.
Yeah, thanks. So the specification on the antibiotics question, maybe you can read it.
Yes, I'm now reading it, yeah. Yeah, okay, so I now understand the question, and thanks for the clarification. I thought it might be going that way, but I wasn't sure. So the question here is, well, it's a viral infection, but people who are sick with viruses are often more susceptible to secondary bacterial infection. This was definitely the case in 1918-19. If you look at the times of death following infection, people either died within a few days of the virus, or they died about 2 weeks later due to bacterial infection 100 years ago. In principle, that's still the same risk here, except we have effective antibiotics, which should be able to save people's lives. I'm not across the details here about, I mean, clearly the more antibiotics we use, the more selective pressure there is, and so we might promote resistance to those bacterial infections. I think, of course, by using those antibiotics, we've got the potential to save those lives. How those things balance out is anyone's guess as far as I'm concerned. And it's certainly not something within my skill set to comment on in more detail.
Okay. So the last question, it's a good one to end with. What are the key questions we need answers for to future modeling?
Right. So I think one of the most interesting things, and I think it was touched on before, is how can we use information on how people are mixing? So with these social mobility indices and, you know, clever things you can do with Google Analytics data and Facebook data. How do we know how that, in a quantitative, rigorous sense, maps across to changes in epidemic transmission dynamics? So it actually kind of picks up on that 1.5 meter question and a few things. To me, this is where we where a breakthrough would make a huge difference, which is knowing how to map those measures of social mobility into changes in the transmission. And we know that they go up and down together, but exactly what that functional relationship is really critical, because that is what will allow us to have more accurate forecasts and predictions, I believe.
Okay, thank you very much, James, and thanks for your time going through all these questions. It was a very interesting presentation. I hope you've all enjoyed it, and we'd like to see you back again in a month's time when Maria Chetnovsky from Princeton University will give a seminar.
Thanks a lot
everyone
for having me. Yeah, hosting.
Right. Have a good day in Australia or wherever you are. Stay safe.
Thank
Bye-bye.
you. Bye.